Now that you can connect to a Luna HSM, let's look at what actually lives inside it, the keys. We'll walk through the main key types, their attributes, and their policies, so you can choose and control HSM-backed keys confidently for your applications. You've already seen what a Luna HSM is, how it's structured, and how clients reach a partition securely. Now we shift from plumbing to payload. Our focus moves to key types, attributes, and policies, so later decisions about key generation and lifecycle are deliberate, not accidental. In Luna HSM, think of a key as vault gold wrapped in rules. The raw cryptographic value is just the center. Around it, attributes define the algorithm, allowed operations, security controls, and whether the key can ever leave the device. Those same attributes determine if your app can encrypt, sign, or wrap keys at runtime. If they're wrong, calls fail even though the HSM is healthy. Solid key templates prevent surprises and harden your applications. Luna keys fall into three main families. Asymmetric keys, like RSA or ECC, come in public and private pairs. They're used for signatures, verification, and secure key exchange, but they're relatively slow. Symmetric keys, such as AES, are single shared secrets, ideal for high-speed bulk encryption, decryption, and key wrapping. MAC or HMAC keys are also shared secrets, but dedicated to proving message integrity and authenticating APIs or tokens. Asymmetric cryptography always comes in pairs, a public key and a private key. With RSA and ECC, the public key is the outside half. It can be exported, shared with partners, and used to encrypt data or verify signatures. The private key is the inside half. It stays in the Luna HSM, is marked sensitive and non-extractable, and is used to sign, decrypt, or derive other keys. Symmetric algorithms are your workhorses for fast encryption and decryption. Today, AES is the default choice. Use AES 2008 or AES 2012-6 for data at rest, key wrapping, and high-throughput workloads, with AES 2012-6 favored when you need long-term protection. Older options like DES and 3DES still appear in legacy systems, but they're no longer considered secure. Keep them only when compatibility demands it, and always confirm what your Luna firmware actually supports. HMAC keys are symmetric secrets used to prove that a message really came from a trusted party and wasn't modified. The application sends its request into the HSM, which combines the request data with the secret key using a hash like SHE256 and outputs a digest. That digest travels with the request. On the other side, the verifier recomputes the HMAC queue. If it matches, the request is authentic and intact without ever revealing the key. Key sizes are all about trade-offs. For RSA, 2048-bit is still widely acceptable, but 3072-bit or above gives better long-term assurance. For ECC, P256 is the default workhorse, while P3884 is preferred when you expect data to stay sensitive for many years. AES-28 is fine for most workloads. AES-256 adds margin. For HMAC, match your key strength to at least SHE256 or SHE-3084 and 512 for higher assurance. When you choose key types, you're really choosing a performance profile. Symmetric algorithms like AES and HMAC are the cheapest and fastest, so they're perfect for bulk encryption and high-throughput authentication. Asymmetric operations cost more. ECC signatures give strong security with moderate latency. RSA, especially with large key sizes, is the most expensive. Always validate these relative costs with benchmarks on your actual HSMs and workload patterns. Mechanism support isn't guaranteed, even across similar Luna HSMs. Start by using PKCS number 11 to query which mechanisms the device actually exposes. Then interpret those results against firmware notes, FIPS mode, and any licensing constraints. Next, compare that list to what your application needs: key sizes, curves, padding, wrapping methods. Finally, enforce all of this in a test environment so missing or restricted mechanisms are caught long before production. Here's how to read this template. CK class and CKA key type say this is an RSA private key. CKA label is your human-friendly name. Use it for stable lookup and versioning like app signing v1. CK token decides persistence. True means it lives on the HSM. False means temporary. CK hivit and CKA sign lock this key to signing operations only. These attributes decide how locked in your key material really is. Private means you must authenticate before using or viewing the object. Sensitive means the raw key bytes can't be read through any normal API. Extractable says whether that key can ever leave the HSM even wrapped. Always sensitive and never extractable act like an audit trail. They tell you the key has been protected, in that state, from the moment it was created. Before you create any key, think like a permissions designer. First, decide the exact operations. Will this key only sign, only decrypt, or just wrap other keys? Avoid mixing roles. Next, choose whether it must persist beyond the session with CKA token. Then define who can use it and whether it may be modified or destroyed. Finally, plan labels and IDs so your application can always find the right key quickly. Treat these as starter templates you can adapt. For TLS or code signing, use an asymmetric private key that's sensitive, non-extractable, persistent, and only allowed to sign or decrypt. For data encryption, use a symmetric AES key. Again, sensitive, non-extractable, persistent, and restricted to encrypt and decrypt. For API authentication, an HMAC secret key is sensitive, non-extractable, and used only for sign and verify. Session keys are short-lived, non-persistent, and destroyed once the workflow ends. Everything we've covered comes down to treating keys as designed security objects, not just bytes in an HSM. First, choose the right key type and algorithm for the role: encryption, signatures, HMAC, or derivation. Then set attributes that lock in confidentiality, usability, and visibility. Validate your Luna policies and mechanisms so theory matches the real device. Next, we'll generate, import, rotate, backup, and retire keys using this design-first mindset.